So disjoint paths and connected subgraphs for H3 graphs. And as I say here, this is joint work with Walter Kern and with Barney and Daniel and Eric Yan. So the first problem we'll look at is disjoint paths. We're given a graph G and a pairwise disjoint set of terminal pairs. And the question is, does G have pairwise vertex disjoint paths P1 to Pk such that Pi is an Si-Ti path for each I in 1 to k? So in this first problem, the number of paths k is part of the input, and in the second k disjoint paths problem, the number of paths k is fixed. And a similar situation for disjoint connected subgraphs. So this time we're given pairwise disjoint terminal sets, and we ask, does G have pairwise disjoint connected sets S1 to Sk, where Zi is a subset of Si for each I in 1 to k. And again, the first case, k is part of the input. In the k disjoint connected subgraphs problem, the number of subgraphs k is fixed. And the first thing we note is that we may assume the terminal sets Zi are independent, since for any instance of disjoint connected subgraphs, we obtain an equivalent instance by contracting edges between terminals in the same set. So an example of the disjoint connected subgraphs problem. So we have our original graph here on the left with two terminal sets, Z1, which consists of these two vertices, and Z2, which is these three. And on the right we have a possible solution. So we take this path of length 3 here, and then this claw here. What do we know about disjoint paths? So disjoint paths is known to be NP complete, but when k is fixed, Robertson and Seymour proved that k disjoint paths is polynomial time solvable. And for special graph classes, disjoint paths is NP complete for graphs of clique width at most 6, and for line graphs, for split graphs, but polynomial time solvable for P4 free graphs. And disjoint connected subgraphs, so even two disjoint connected subgraphs is known to be NP complete, and also again NP completeness for split graphs. A quick reminder, a graph G is said to be H free for some graph H if G has no induced subgraph isomorphic to H. So this diamond graph here has an induced triangle in the blue vertices, but no induced C4. So for example, we have this middle edge. Our results, so combining new results with these known results that we've looked at, we get a complete dichotomy for k disjoint connected subgraphs, and an almost complete dichotomy for disjoint paths and connected subgraphs. So our first theorem, we let H be a graph, and if H is an induced subgraph of SP1 plus P4, then for every k at least 2, k disjoint connected subgraphs for H3 graphs is polynomial time solvable. Otherwise, even two disjoint connected subgraphs is NP complete. And theorem 2, we let H be a graph which isn't any of 3P1, 2P1 plus P2, or P1 plus P3, and if H is an induced subgraph of P4, then disjoint connected subgraphs is polynomial time solvable for H3 graphs. Otherwise, even disjoint paths is NP complete. And now we look at the proof of theorem 1. So we break this down into a number of smaller results. So first, we find NP completeness for line graphs, and hence for claw-free graphs. Then NP completeness for bipartite graphs and graphs of high girth. It gives us NP completeness where H contains a cycle. Then we use this known result about split graphs, and then we give the polynomial result for P4 plus SP1 free graphs. So the first case, as we said, this NP completeness result for split graphs deals with the cases where H contains 2P2, C4, or C5. And so what remains is the case where H contains a claw, a triangle, or H is contained in P4 plus SP1. So first we look at claw-free graphs, and for this we reduce from 3SAT to 2 DCS for line graphs. So this graph here is the graph for which we look at disjoint paths in the line graph. And we won't go through the reduction in full, but we'll give the basic idea. So what we have is basically some subpath for each literal, and then these clause vertices, which are each adjacent to each literal contained in the clause. And we take two terminal sets, one consisting of these two end edges E and F, so remembering that these will be vertices when we work in the line graph, and the other consisting of each of these edges incident on the clause vertex. And the basic idea is that to connect these edges E and F, we'll use a path corresponding to the false literals, which will leave the true literals to connect the clause vertices. Then the case of triangles, as we said, comes from the stronger results about bipartite graphs of girth at least G. And these are obtained straightforwardly. We just reduce from 2DCS by subdividing edges D times. And finally, the polynomial results. So we're looking at K disjoint connected subgraphs for P4 plus SP1 free graphs. So a solution is of the form, or consists of these subgraphs Si, where the terminal set Zi is contained in Si. And because our graph is P4 plus SP1 free, each of our components Si is either P4 free, or it contains P4 plus RP1 for some maximal R at most S minus 1. And what we want to show basically is that each of our subgraphs Si has some small dominating set. So if Si is P4 free, then we have this well-known lemma saying that P4 free graphs have spanning complete bipartite subgraphs, and since we can assume that our terminals are independent, Si must contain a vertex dominating the terminal set Zi. Otherwise, since R is maximal, Si must have dominating P4 plus RP1, and we have this folklore result which says if we have this dominating set which has size, I guess, at most S plus 3, then we can find some connected dominating set of size at most 3S plus 1. So what our algorithm does, we just try each possible set of 3S plus 1 vertices to form the dominating set for each of our terminal sets from 1 to K, and decide whether it leaves each Zi connected. And we can see that this runs in polynomial time because both K and S are phased constants. So this finishes the classification for K disjoint connected subgraphs. And moving on to our second theorem. So we remind ourselves we're looking at H being any graph not contained in 3P1, 2P1 plus P2, P1 plus P3. And we want to show that if H is an induced subgraph at P4, then disjoint connected subgraphs is polynomial time solvable for H free graphs. Otherwise, even disjoint paths is NP complete. So again, we split this down into a number of smaller results. So the first one, NP completeness for line graphs, gives us NP completeness for clause free graphs. Then we want to find NP completeness where H contains a cycle. Again, we have this known result about split graphs. And finally, this case of 4P1, P1 plus P4 free graphs. So we start with the line graphs, and this is a straightforward reduction from a known result about the edge version edge disjoint paths. Then again, in the case where H contains a cycle, we have the stronger result for graphs, bipartite graphs of high girth, and again we use the subdivision trick. Now looking at the result for split graphs again. As we said earlier, this gives us NP completeness for graphs for H containing 2P2, C4, or C5. And so we're left with our final result, 4P1, P4 plus P1 free graphs. And the reduction here uses the reduction which shows NP completeness for split graphs. So when we look at this result, we see that the split graph G has the property that the independent set is exactly the set of terminal vertices. So what we do is we add edges Si, Sj, and Sitj for each I not equal to j, so that now the clique remains a clique, but what was the independent set is now a complete graph minus a matching. So in other words, it's 3P1, P2 plus P1 free. So this tells us that our new graph is 4p1, p4 plus p1 free. And we're left to show that this graph is a yes instance if and only if our original graph G was. And this is straightforward to see because all of the edges we've added contain two terminals in different terminal sets. And therefore these edges can't be used in any solution. So G dash is a yes instance if and only if G is. And now we look in more detail at the open cases for Theorem 2. So initially we have 6 open cases, 3 for each of our 2 problems, 3p1, p1 plus p3, and 2p1 plus p2. And what we show now is that we can reduce the number of open cases from 6 to 3. So first we show that disjoint paths and disjoint connected subgraphs are equivalent for 3p1 free graphs. And this is straightforward. Well, any instance of disjoint paths is an instance of disjoint connected subgraphs. And since we may assume that our terminals are independent, if our graph is 3p1 free, then our terminal sets must have size at most 2. So in other words, we're looking at disjoint paths. And then the more complicated case is the p1 plus p3 free graphs. So we're going to show that disjoint paths and disjoint connected subgraphs for p3 plus p1 free graphs are both equivalent to disjoint paths for 3p1 free graphs. And looking at it, since 3p1 free graphs are p1 plus p3 free, and any instance of disjoint paths is an instance of disjoint connected subgraphs, we just need to reduce disjoint connected subgraphs for 3p plus p1 free graphs to disjoint paths for 3p1 free graphs. And to do this, we'll use this result of Laurier, which says that p1, the complement graphs avoiding the complement of p1 plus p3 are either triangle free or complete multipartite. And what this tells us we can do, given our p3 plus p1 free instance, is partition our graph into sets d1 to dp, where p is the number of connected components of the complement of G. Each set di is either 3p1 free or the disjoint union of complete graphs, and di is complete to dj for any I not equal to j. So first we'll argue that we may assume each terminal set has size 2. So in other words, we'll reduce disjoint connected subgraphs for p1 plus p3 free graphs to disjoint paths for these graphs. So the first thing to do is, since each terminal set is independent, each terminal set must be contained in one set dk. And if this dk is 3p1 free, then as we said earlier, our terminal set must have size at most 2. Otherwise, our set dk is the disjoint union of complete graphs, and since our terminals are independent, each one lies in a different complete graph. So this being the case, we need at least one vertex from outside of dk to connect our terminals, and because di is complete to dj for I not equal to j, any one vertex from outside of dk will do. So therefore we may assume z1 has size 2. Zi has size 2. So now that we've reduced disjoint connected subgraphs to disjoint paths for p1 plus p3 free graphs, we now want to reduce disjoint paths for p1 plus p3 free graphs to disjoint paths on 3p1 free graphs. And what we'll do is divide our solutions into 2 types. So the first, where every solution path has length 2, and the second, where there exists a solution path of length 3. So note that 3 is the maximum length because our graph is p1 plus p3 free. And the first thing is that since any 2 3p1 free sets, say di and dj, are complete to each other, we can merge them into one larger 3p1 free set. So we can assume we've only got one set which is 3p1 free but not necessarily the union of complete graphs, and that's d1. So now finding a solution of type 1 is equivalent to finding a perfect matching in this bipartite graph we describe here. So we let A be a part containing one vertex for each terminal pair, and B the set of non-terminal vertices of G. with an edge xy if and only if the vertex y is adjacent to both vertices in the terminal pair x. Otherwise, if we don't have a solution of type 1, we know we must have some solution contained in D1, which is a path of length 3. And in this case, we create a new graph G prime as follows. So we let A1 be the set of all the terminals in D1, A2 the non-terminals in D1, and B1 the terminals of D2 to DP, and B2 the non-terminals of D2 to DP. The edges are then as follows. So for each terminal pair SI-TI in B1, we add all edges between SI and B2, but delete all edges between TI and B2. Then we add an edge between every pair of vertices of B1 belonging to different terminal pairs, and an edge between any two vertices of B2. So these new edges in B1 union B2 ensure that our graph G prime is 3p1 free. And now we want to show that we have an equivalent instance of disjoint paths. So first we assume we have a solution S as P1 to Pk in G, and we assume that this solution contains a minimal number of paths of length 3. So if this isn't a solution in G prime, it must be that we've deleted some edges which are contained in one of our solution paths. And if this is the case, this edge must be part of some path SIUTI, where SITI is contained in B1. But we know, because we've already said there is no solution of type 1, that there exists some path of length 3, say SJXYTJ, contained in D1. The problem we have now is that we said we had a minimal number of paths of length 3, but if we swap the role of U with X or Y, we'll have fewer paths of length 3. So if, for example, we say we want SIXTI and SJUTJ to replace these two paths, then we have fewer paths of length 3. So this is a contradiction, and it must be that any solution in G is also a solution in G prime. Then the other direction, well, imagine we have some solution in G prime. If this isn't a solution in G, it must make use of some edges that we added. But in G prime, every non-terminal neighbour of a terminal vertex Ti is contained in A2. And since we didn't delete any edges incident on A1 or A2, this path must exist in G. Similar for any terminal set contained in A1, which used a path which left A1 union A2, and obviously the same for any path which was completely contained in A1 union A2. So we've shown now that disjoint paths for P3 plus P1 free graphs is equivalent to disjoint paths for 3P1 free graphs. And having already shown that disjoint connected subgraphs for P3 plus P1 free graphs was equivalent to disjoint paths, we're done. So as we've just seen, the open problems that we're left with are disjoint paths for 3P1 free graphs and for P2 plus 2P1 free graphs, along with disjoint connected subgraphs for P2 plus 2P1 free graphs. And these seem difficult. We haven't managed to make full progress on them. But one thing we have been able to show is that disjoint paths is polynomial time solvable for code bipartite graphs, which form a subset obviously of 3P1 free graphs.